Okay. So we've been talking about the graph of a polytope, and well, we already discussed that generally the graph of a polytope can tell you a little bit about the polytope, but maybe not a lot. And one thing that we know for sure is that there are different polytopes that have the same graph. We saw that a prominent example of that is the cyclic polytope. So if you the graph of the cyclic polytope is the complete graph, and so you have all different kinds of cyclic polytopes that have the same graph. Okay, and so that means that in general, if I give you a graph, then there is no way that you're going to be able to recover the polytope that it came from, if there is such a polytope. Okay, but what I want to tell you about today is that under certain conditions, it is possible to recover the polytope from the graph. And that condition is the condition of being simple. Okay? So that's the theorem that I want to prove today. For simple polytopes, the graph determines the polytope. In other words, if you have that P and Q are simple polytopes that have the same graph, then you're going to be able to deduce that P and Q are actually the same polytope combinatorially. Okay? Now remember that what we mean when we say that two polytopes are the same combinatorially is that they have the same lattice of faces, same phase lattice. Okay. So that's the theorem that I want to prove today. Maybe I'll tell you a little bit about the history of this before we start. This was a conjecture of Pearl's from 1970. And this was actually open for a long time, until 1987. So it took 17 years for this to be settled and to be proved true. And that was done by Blind and Mani. And the proof that I'm going to show you is from a year later, from Kalai. And I think it's pretty remarkable that this was a problem that was open for 17 years, but I can give you a proof in an hour. So I think that points to the fact that sometimes, especially in a field that is relatively new, maybe some of the big open problems, maybe you just have to look at them in the right way. I think Ziegler says that it's kind of embarrassing to read Kalai's proof and think that for 17 years nobody thought of it. Somehow, if you already, it's that kind of thing where maybe if I gave it to you as a homework problem, maybe you would solve it because you don't know that it's open. And maybe it's helpful not to know that it's supposed to be hard. I don't know. Anyway, so that's what we're going to prove today. And let me first remind you that P is simple, so that a D polytope a D polytope P is simple if every vertex has degree D, and what I mean by degree is the number of edges coming out of it. Okay? And you should remember that actually this is a pretty strong property, because it says that if I have my polytope P, and here's a vertex V, okay, and this is meant to be a d-dimensional polytope, then we're living in d dimensions, and we have d rays coming out, and that means that these rays are going to be linearly independent from each other. So that means that if you look at this cone, it's actually a cone over a simplex. So remember the name we had for that is vertex figure. If you make a little cut here, then you're going to find that this is a simplex. Okay. And so that means that, for example, that means that every subset of the rays forms a face, right? So in this case, if you take these two rays, they form this face. If you take these two rays, they form this face. In other words, if you look right at V, then what you're going to see is basically something that looks like the positive orthant. Okay, you have D rays, but it's D rays that are forming like a positive orthant. Okay, that's what it means to be simple. And maybe the next thing that I will point out then is that, I don't know, if you hope this to be true for any family of polytopes, then actually it's natural to hope that it will be true for simple polytopes. The reason being that, like we said, one problem is that the graphs of polytopes can have a lot of edges. Right? So for example, a lot of polytopes, neighborly polytopes, have all vertices connected to each other, too many edges. And this is exactly the opposite extreme. These are the polytopes that have the fewest number of edges, right, for a fixed number of vertices. Right? Because you know that at every vertex, if you're d-dimensional, you need at least d edges, and this is saying, well, you have the smallest possible number of edges. Okay. So somehow, what this is saying is that if your graph is not too busy, if it doesn't have too many edges, then you have more of a hope of having this theorem. Okay. So that's what we're going to prove. Okay. So the proof goes as follows. Let's consider the set of all possible acyclic orientations of the graph. And remember that what this is that you're going to assign directions to each edge in such a way that you're not forming any cycles. Okay? So maybe we can do an example. So that's an example of a polytope, a simple polytope, right? It's a three-dimensional polytope where every vertex has degree 3, and I'm going to orient each edge in some direction, okay? But I want to make sure that I don't form any cycles. So for example, because I oriented it this way and this way, then I don't want to close a cycle, so I have to orient this guy this way. Okay. So if I did this carefully, if I did this correctly, then you should not be able to find any cycles in this graph. Okay. One thing that you should notice is that from an acyclic orientation, you get the structure of a poset on the vertices. Okay, and that is obtained by saying that if you have an edge from one vertex to another one, then the source is less than the sink. So I'm going to say that U is less than V if I have a way of walking from U to V. by following the directions of the edges. Okay? Now, one thing that you should notice, this is a poset because you cannot have u less than v and v less than u. Because if you had u less than v, then you could walk from u to v. And if you had v less than u, then you could walk from v to u and complete a cycle. But because we have no cycles, then you cannot have both u less than v and v less than u. So this, and the other property that posets need to satisfy is that if u is less than v, you can walk from u to v. V is less than w, so you can walk from v to w. Then u is less than w because you can walk from u to w by joining those two paths. Okay? So that's why you get this poset structure. Yeah. That's correct. So you have to put an orientation on every edge. Does that worry you? I could.
Well, they're obviously different than a set of spanning trees, but is there some sort of definition for like orienting?
There is another one to get into it, but I'm happy to discuss it with you. But I mean, in a spanning tree, you could orient it in any way, and you can't form cycles, so it's going to be acyclic, basically.
Yeah, but you don't have to use every edge.
Right. Yeah, here I need to orient every single edge. That's right. Okay. So for example, here, well, let me make a definition. So definition, say that an orientation is good if for any face f of p the orientation restricted to the face has a unique sink. So I'm going to say it's good if I have this property, and it's bad otherwise. Okay? So let's look at this orientation that I have here, and let's figure out if it's good or if it's bad. How many sources do I have in my graph? So remember, a source is something such that everything is directed out of it. It's a vertex such that everything is directed out of it. And here you'll see that the only source is this one. Source. How many sinks do I have? So a sink is something where a vertex where everything is coming in, and if you look, you'll see that it's only this one. Okay, so it is true that that this orientation has a unique sink. But I have to check not only that, I have to check that for any face. Okay. So for example, let's look at this triangular face. Does it satisfy the property that it has a unique sink? Yes, right? This is a source. This is neither a source nor a sink. And this is a sink if I forget about everything else. So this face satisfies it. Okay. What about the back face? Wait, I did my picture wrong, I think. I meant to do it like, I meant to orient this like this. Now notice that in the original graph it's still true that this is the only source, this is the only sink. Wow, I did this all wrong. Okay, well, anyway, so hopefully you get the point. Even if I drew my example wrong, that you have to check this property not only for the whole orientation, but for the orientation restricted to every face. Okay. Oh no, actually. So let me also answer your question, but let me point something out. Well, let me answer your question first. So before I had it like this. And in the blue face, according to this orientation, I have a unique sink, which is this one. And I think if you check all the faces, you're going to find that they all have a unique sink. Yes. So this is a good orientation. Okay. So there's nothing wrong with it. It's a good orientation. But what I wanted was to show you a bad orientation, which is why I changed my mind. So if instead I change this to be going in this direction, then actually for the big graph, I have another source, but that's fine because I only care about sinks according to this. Okay. But then this is a sink. Okay. Anyway, so this is a bad orientation. But my point is that to check whether it's good or to check if an orientation is good, you have to do this check for every single face, like we did for the purple orientation, and we got a good orientation. Okay, that's what it means to be good. Let me point something out, which is that if I take a generic vector, remember that induces an orientation. Okay. The induced orientation O sub C is good. And if you think about why that is, well, here I have my polytope P. Let's say that the orientation is, let's say that the direction C is C. Let's say that you take some face. Okay, so maybe this is the face that you're going to consider. And you know that the orientation that C induces on F is just the orientation that we discussed in linear programming. Okay? And that means that this orientation is going to have a unique sink. And which sink is that? It's basically the vertex where the function C obtains the maximum value. Right? It's the farthest vertex along this direction. And because C is generic, we have a unique such vertex, so that's the unique sink. Okay. In this case, it would be out of the face F, the vertex maximizing C. Okay. So these orientations that we got from directions, they're all going to be good. Okay. Okay. So how do you tell a good orientation from a bad orientation? Turns out that actually there's something you can do. I mean, one thing you could do is just for each orientation, for each face, do this check. But you can do something different, which is the following. I'm going to define, for each orientation, I'm going to define a number, and it's going to be the sum over all the vertices of 2 to the in degree of the vertex. Okay? So maybe Maybe let's forget this orange thing that I did here. Let's go back to the purple orientation, which was like this, right? And then, so out of this orientation, I get a number, right? And what is the number in this case? Well, you just look at each. Here you say, what's the in degree of this vertex? 0. So 2 to the 0 plus. And in degree is number of edges coming in, yeah? So here there's one edge coming in. Here there's 2 edges coming in. Here there's 2 edges coming in. Here there's 1 edge coming in. And here there's 2 edges coming in. No, 3 edges coming in. So I compute this number. 8, 10, 14, 18, 19, 20. No. 21. It better be odd because I have only 1 and everything else is the end. So I compute this number. I claim that just from that number you can tell if the orientation is good or bad. Okay? That's what I'm going to show you. So my claim is that if the orientation is good, then this number is the number of non-empty faces of the polytope. So how many non-empty faces do I have here? I have 6 vertices. Help me keep track of this because it's hard to do this in my head in front of all of you. 6 vertices, right? How many edges do I have? 4, 8, 9. 6 plus 9, 15. How many faces do I have? 5. And I had 15. So I have 20. And then the whole thing, 21. Thank you.
So is the sum of your poset lattice connectivity minus the intercept?
It's just the number of vertices in the poset minus 1. Yeah. And I claim that if O is bad, then F0 is bigger than this. Bigger or smaller? Yeah. Bigger than this. Okay. So just by computing that number you can tell. So here's how I'm going to prove this claim. Number of non-empty faces is less than or equal to the following thing. Is less than or equal to the number of pairs FV such that F is a face of P and V is a sink of F in the orientation. So let O be an orientation. So the number of non-empty faces is less than or equal to the number of pairs of a face and a sink in that face. Why is that? You see here, I'm just computing for each face, I count it once. And here for each face, what I'm doing is that I'm counting the number of sinks in that face. Okay? So really what I'm saying here is that every face has at least one sink. Why is that true? Because in any acyclic orientation, you have to have sinks. Right? Because if you just start walking forward in an acyclic orientation, then you must get stuck somewhere because there's no cycles, and if you get stuck, that's a sink. So here I'm saying the number of sinks is at least 1. Okay? Okay. But now, if you think about it in the other direction, let's fix a vertex V. How many faces are there such that... Okay, so let me write it like this. For each vertex V, number of faces F for which V is a sink. Okay? How many faces are there for which V is a sink? Our vertex is V. It has some incoming edges and some outgoing edges. Right? And I need to figure out for how many faces is V a sink? Which ones? Uh-huh. But you have more than that. Immediately you have that. What is less immediate but also true? So maybe let me first repeat what you said. For the vertex itself, the vertex is a sink. For all of these edges, that vertex is a sink. Now you're saying that every pair of edges forms a face, determines a face for which that vertex is a sink. Right. But why stop at pairs? Also for the three vertices, there is a three-dimensional face there, and this is a sink. And that's exactly it. If you have T edges here, then because the polytope is simple, that means that you have a simplicial cone of dimension T, where any subset of those T guys forms a face for which this is the sink, because everything is pointing in this direction. So what I get is exactly 2 to the number of edges going in. Two to the number of edges going in, which is exactly the n degree of V. And that's exactly this number FO. Okay? So it's definitely true that FO is greater than or equal to this. When is it equal? And when is it not equal? Well, you're going to have all of these are equalities, so the only place where you have inequality is here. You're going to have equality if every single face has exactly one sink. And that's exactly the definition of being good. Okay? So if the orientation is good, then you have equality in every single step. And if F is not good, then for at least one of these things, it's a strict inequality. Okay? So that proves this. So that's a nice slick argument to say that you can basically tell the good faces from the bad faces just by computing this combinatorial number. So you see, you can tell just from the graph. Maybe let me say this a little bit more concretely, because the point is that if you look at the graph, you don't know what this number is, right? You don't know what the faces of P are just from looking at the graph. But the point is that if you just have the graph, then you're just going to look at all the possible orientations, and you're going to compute this number for each of all the orientations. Okay? All the orientations that are good are going to have the smallest number FO. All the orientations that are bad have a bigger FO. Okay? So the point is that the good orientations O are those for which this number FO is minimal, is smallest. Okay? So just from the graph, you can tell what's good and what's bad. Okay. And think about it. That's very surprising because the definition of good talks about faces of the polytope. So it seems like a geometric definition, but actually this is telling you that you can tell goodness combinatorially. You don't need to know what the faces of the polytope are. So that's the nice observation about this. That's why this observation is so nice. Okay. So that's the first step of the proof. Now, for the second step of the proof, I need to make a definition. So we're going to say that a graph is k-regular if every edge has degree k. So for example, the graph of a simple polytope of d dimensions is going to be d-regular. Okay? But the other thing that you should notice is that if you look at any face of a simple polytope, that's going to be a simple polytope. This is another one of these nice facts. It's true, it's not obvious, and you should think about how to prove it. And if you see it right away, great. And if you don't see it right away, then think about how to prove it. Yeah? Every vertex has degree k. Thank you. And so the point then is that if you look at the graph of a particular face of dimension k, that subgraph is going to be k-regular. Okay? So if f is a face of p, then if you take the graph of p and you restrict it to the vertices in f, then you're going to get the graph of f, which is k-regular, where k is the dimension. Okay. But again, it's very important here that because p is simple, then any face of p is also simple. And that's why you can know this. Okay. So then here's the next observation. I mean, the way that you should think about what I'm going to say next is this. We're trying to recover a polytope from its graph, right? So in other words, I'm giving you some picture of a graph, and it's kind of like the skeleton of the polytope. And what you need to know is basically what faces to fill in and what faces not to fill in. Right? And this is going to tell you how to know that. How to tell faces from non-faces. For example, you're looking at this picture and you know that this blue thing is a face. Your brain is telling you that, but how do you know? Or for example, your brain is telling you that this hexagon is not a face, right? But how do you know? That's what we need to figure out next. How do we know, looking at this picture, that there's no hexagonal faces, that the polytope is really the one that you're visualizing? So this is what's going to do it. Okay. And how do you do it in general? Like this. Consider a subset of the vertices. And the question is, do those vertices form a face or not? So the vertices of U form a face of the polytope if and only if the following is true. Two things. The graph of P when restricted to U should be K regular, and there should exist a good orientation O such that let me just draw this schematically. Here are all the vertices. Here's maybe U. And in the orientation, all the edges should point out of U. No edge points from V minus U to U. Okay, that's the claim. So all the edges that connect a point in U and a point not in U have to go from U to out of U. So this is a bit of a strange condition, but the point that you should realize is that, again, this is a geometric condition, right? This is saying, do I have a face or do I not have a face? And that, that means there's a linear function such that blah, 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 blah. But this condition doesn't at all refer to the polytope. It only refers to the graph. It's saying the graph is K-regular, and that's a property of the graph only. And then it says something about being able to orient the graph with a good orientation. But we just saw that the goodness of an orientation can be read from the graph. Okay? And so by proving this claim, we're going to be done. Because we're going to be able to say, we can tell exactly where the faces are through a completely combinatorial criterion. Okay? And this is going to be what proves this theorem. So that's the point. This is geometry, and this is combinatorics of the graph. And so what I just said is that the claim implies the theorem. So we just need to prove this claim. But before I prove this claim, let us test it on that graph, okay? Because so Matthew gave us a very good reason for why this hexagon is not a face. But for some reason, this is not really what this theorem is saying. But this theorem should also be able to answer the question of why that hexagon is not a face. Okay? So why is this hexagon not a face?
Edges that are not
The answer is yes. So this is the graph, right? And this is U. U is all the vertices. And I have to check two conditions. The first is that the graph is k-regular. Is it? Is this a k-regular graph? Yes. It's 3 regular. The second condition, there exists a good orientation such that no edge points from v minus u to u. Does it exist? It does, Dito. Which one? That's an example of an orientation that has no edges from v minus u to u. So that's telling me that actually this is a face. So where are we supposed to prove that this is not a face? You see, the thing is that what this is saying is the vertices of U form a face of P. Is it true that these vertices form a face of P?
Yes.
It is. It's the whole polytope. Okay, so that's not how you're going to discard that. So how do we then know that that's not a face? That the hexagon is not a face?
It won't be k-regular if you're looking at it in a competition. Because it has to be dimension 2. K is supposed to be the dimension of your face. It's not a two-dimensional face.
If you're testing it to be a two-dimensional phase, then you need to be 2 regular. Maybe it's a little bit clearer if I just say here K phase. Yeah?
Could you go ahead and draw the cube as an example where we would need the second condition?
Could I? So here's the cube. So how do I know that these 4 vertices don't form a face? What does the first condition say? So this is U, these 4 vertices. So what does this look like? I have 4 vertices. These 2 are connected. These 2 are connected. And there's no other connections between them. Is this K regular? I guess it is. It's 1 regular, right?
We know it's simple. So you don't want to have 2 vertices that you're going to do this one dimension.
Right. Now let's see what the other condition says, just so you see what the other condition looks like. If this was a face, then there should be a good orientation so that all the edges between U and not U have to point out. So that means that there should be a good orientation such that this points out of U, 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 and this points out of U, this points out of U, this points out of U, this points out of U. What about these 2? We can't tell. That this criterion doesn't say anything about that. So why can this not be the beginning of a good orientation? There's going to be 2 sinks. Why?
Because if you are in one half of you, you can't get to the other half of you.
Right. Another way of saying that is that, look at this edge. It has to point either this way or this way, meaning either this is a sink or this is a sink. And also this is a sink or this is a sink. So that would give us 2 sinks, which means that this is not a good orientation. So that's how this claim can tell that this is not a face. Okay?
Possible that you don't do the second condition multiple times.
If you took the hexagon as the sort of the outer vertices of that hexagon cube, so
Right. So Matthew's suggesting that we could also do this for if I'm understanding you correctly, that we could also use this for these 6 vertices.
Yeah.
And that's an example of a collection of 6 vertices such that the induced graph is too regular, which would be the dimension of that phase. It's just that the good orientation doesn't exist. Because according to the good orientation, both of these vertices would have to be sinks. Yeah. Okay. Well, I wanted to prove this for you, but I actually think it's more important that you understand it than that you know how to prove it. What we're going to do is I'm going to prove one direction for you, and I'm going to ask you to read the other direction. So let's prove this direction. Suppose that you actually have a face. Okay, so maybe here's you, and then here's the rest of the polytope. And I need to make, well, okay, so suppose that U forms a face, a K face. Then the first condition is true, right? Because if I restrict to U, I'm just going to get the graph of the polytope U, which is K regular, since U must be simple. Okay, I'm just repeating the argument over there. So the first argument, the first condition holds, okay? Now, for the second condition, what I'm going to do is that I'm going to, I need a good orientation that points out of U, basically. And we know that a nice way to build good orientations is from generic vectors. Okay? Now, which vector would you naturally start from? Well, a phase means that you have a vector pointing to it. So let's start with a let U be the phase in direction minus C, right? So the one that minimizes C. Okay. And I would kind of want to say that this induces the orientation, but what's the problem with that? The problem is that it's not generic, and it's definitely not generic because here you see a phase that's minimizing. So how do I fix that? Kind of move it a tiny bit. So let D be C plus some tiny perturbation, epsilon times C prime, where epsilon is really, really tiny. Okay? The effect of that is basically that you're going to break because the problem is that all of these vertices have the same value, the same dot product with C. If you perturb a tiny bit, then you're going to break that tie between all of these 4 guys, but you're going to break it so slightly that still all of these 4 guys are going to be smaller than all of the other guys. Okay? So then the point is that this orientation is what we're looking for. Is good and points out of U. Okay? So that proves one direction. And the other direction actually is not much harder, but I don't want to keep you guys late. So I'm going to ask you to read the other direction. And that will prove this theorem. Okay? Now, one thing that I'd like to point out to you guys actually is that it seems that there is no good algorithm for doing this. Okay, so here's a criterion, but this criterion is not really applicable in practice because if you know anything about algorithms, this is an exponential time algorithm, and that just means that if you try to run it on a big polytope, it's going to make the computer crash. Okay? So an open problem that I think is interesting would be to look at this more carefully and see if you can tweak the argument into an algorithm that is actually efficient in practice. I think no one knows how to do that. At least as far as when the book was written, no one knew how to do that. So, all right.